Sometimes the disaster isn't the storm, it's a missing column. In seconds, a single floor can vanish, and the weight it carried slams onto its neighbors, boosting their load by 30% or more. Most buildings survive small mistakes, but when redundancy fails, collapse travels like dominoes, floor by floor. What turns one hidden weakness into a total structural disaster? Let's break down the mechanics behind a chain reaction you never see coming. Every building stands because its weight, its load, is carefully routed down through slabs, beams, and columns, all the way to the ground. This invisible journey is called the load path. Each part carries its share, but the system only works if the connections and paths are uninterrupted. Engineers build in redundancy, backup routes for the load, so that if one piece fails, others can take over. That is the difference between a single point of failure and a robust, redundant structure. When a column or wall is lost, the weight it once carried does not disappear. Instead, it shifts, often suddenly, to neighboring elements. Imagine a column holding up 4 floors. If it fails, its load, 800 kilonewtons, gets divided between the columns on either side. Each one now takes on about 33% more than before, jumping from 400 to 533 kilonewtons. This is where reserve capacity matters. Most columns are designed to handle 30 to 50% beyond their normal load, buying precious seconds for the structure to adjust. But if the extra demand overshoots that margin, the backup columns themselves can fail. The overload moves outward like ripples from a stone in water, threatening the next set of supports. This chain reaction is called progressive collapse. The danger is not the weight itself, it is the sudden loss of a path and the domino effect that follows. In a well-designed building, alternate load paths and reserve capacity act as shock absorbers. Without them, one floor's failure can become a total collapse. That is a disproportionate collapse when a small local failure causes a much larger section or the whole building to fall. Key engineering terms explained clearly. Load path, the route that a building's weight follows from slab to ground, through beams and columns. Redundancy, backup routes or extra elements that carry load if a primary path fails. Disproportionate collapse, when a local failure causes a much larger section or the whole building to fall. Progressive collapse, a chain reaction where one failure triggers others and spreads through the structure. Slab-column connection, the junction where a horizontal slab meets a vertical column and transfers load. Punching shear, a localized failure where a column pierces through a flat slab because of concentrated load. Ductility, the ability of materials or elements to deform without sudden failure, giving warning and allowing load redistribution. Continuity ties, reinforcement that links elements together so loads can be transferred around a loss. Reserve capacity, the extra strength built into elements so they can carry more than their usual load. Inspection regime, a planned schedule of inspections to find corrosion, water damage, and other long-term problems. Hard lessons, connections matter more than raw strength. Small changes can create single points of failure. The building often warns you with cracks, deflection, or unusual sounds. Plan for reserve capacity and a rigorous inspection regime, always. Safety is not one strong element, it is many weak ones backed up. Would you notice the warning signs or trust the building until it was too late? A building can lose its strength in 4 main ways, each one a potential starting point for disaster. First, a sudden blast, like a gas explosion, can unleash enough pressure to rip out a wall or column in seconds. Just 5 to 10 pounds per square inch is enough to eject a concrete panel, instantly breaking the load path. Second, hidden flaws in connections can lurk for years. If welds or anchors are too weak, or if critical joints crack, the structure loses its ability to share the load. The FIU bridge collapse in 2018 began with cracks at a key node, dropping the bridge's strength by at least 20% before anyone acted. Third, overloading from construction changes or unplanned weight can erase the margin of safety. Adding heavy equipment or rooftop units can triple the design load of a slab. At the Sampoong Department Store, HVAC units and a helipad pushed columns far beyond their limits, setting the stage for failure. The warning signs, a widening crack, a stuck door, are often ignored until it is too late. Fourth, long-term corrosion and deterioration eats away at a building's core. Water and salt corrode steel, spall concrete, and shrink the strength of rebar. At Surfside, inspections found up to 40% loss in rebar cross-section. When enough steel is gone, the slab can no longer grip the column, and punching shear takes over. The slab gives way suddenly, as if a cookie cutter stamped out a chunk of floor. That is the weak point where collapse can start and spread. Inspections are the last line of defense. Miss a growing crack or a patch of rust, and the building's reserve capacity may already be gone. One lost column can be a domino. At 5:45 a.m. on May 16, 1968, a gas explosion tore through Flat 90 on the 18th floor of Ronan Point, a newly built tower in East London. The blast pressure, somewhere between 5 and 15 pounds per square inch, was enough to blow a 1.2 by 2.4 meter precast concrete wall panel clean out from the building corner. In that instant, the load path was broken. The floors above, suddenly unsupported, dropped onto the ones below. 4 stories of the southeast corner collapsed straight down in a matter of seconds. Survivor accounts collected by the inquiry describe a sound like thunder as the panels separated, one after another. The investigation found that the panels were joined with dry mortar joints, not continuous reinforcement. Some connections were filled with debris or even newspaper, not concrete. There were no continuity ties running through the panels to hold the structure together if one part failed. The strength of each panel was never the issue. Each was rated for more than 1.5 times its normal load. But the joints, the very links between panels and slabs, had almost no reserve capacity. When one panel left its place, nothing stopped the chain reaction. This was the first time the term disproportionate collapse appeared in a British building inquiry. The damage from a single missing panel reached far beyond the original blast zone. The official report called for new rules. Every connection had to be strong enough to resist both normal loads and accidental events, and continuous ties had to bind the structure in every direction. In the end, the lesson was clear. Connections, not size, decide collapse. June 29, 1995. In Seoul, the Sampoong Department Store was open for business as usual. By mid-morning, staff noticed cracks running across the 5th floor slab. Engineer Kim Seon-wook inspected the damage at 10 a.m. and warned that the cracks were growing wider, up to 10 centimeters by late afternoon. Doors near the south wing began to jam. Columns showed signs of bowing, but the store's manager, Lee Han-sang, refused to evacuate. Shutting down would mean a day's lost revenue. Instead, maintenance teams tried to patch the cracks and keep the store open, even as creaks echoed through the building and customers complained about shaking floors. The building's original design had already been compromised. Columns, meant to be 80 centimeters thick, were slimmed down to 60 centimeters for extra retail space. A rooftop helipad and 3 massive heating, ventilation, and air conditioning units, each weighing 15 tons, had been dragged across the roof and left above key columns, overloading the structure by as much as 3 times its intended capacity. No additional reinforcement was added. The slab column connections, the critical joints where flat slabs meet vertical supports, were never upgraded. At 5:52 p.m. KST, the slab above the 5th floor punched through around a single overloaded column. Within seconds, the south wing's columns buckled. The floors pancaked downward in a cascade, each impact multiplying the load on the next. In less than 20 seconds, half the building had collapsed. Ignoring cracks is not harmless. It changes the load path. Decisions made in offices and boardrooms can erase reserve capacity, turning a single flaw into a catastrophic chain reaction. The building had spoken for hours before it fell. No one listened. When a single floor drops, the collapse does not pause to negotiate. The load that once traveled safely down is forced sideways, slamming into neighboring columns and slabs. At first, this redistribution is static. Each adjacent support takes on 25 to 35% more weight. But the real danger comes next. As the fallen floor picks up speed, it strikes the level below with a force far beyond its own weight. Engineers call this the dynamic amplification factor. In a pancake collapse, this impact can multiply the load 4 to 6 times over, crushing the next floor in a split second. The process repeats, floor after floor, like dominoes falling in rapid succession. Without ductility, the ability of materials to stretch and absorb energy, the structure shatters rather than bends. One hard lesson: when redundancy fails, a single missing link can turn a building into a stack of dominoes. Defense against progressive collapse starts with the details that hold a building together. Continuity ties, steel bars running through floors and walls, link the structure so loads can reroute if a section fails. Compartmentalization uses shear walls and fire barriers to box in damage, stopping one failure from spreading unchecked. Regular inspections are not optional. Any crack wider than 0.3 millimeters or signs of exposed rebar signals the need for immediate review. Engineers rely on an inspection regime, scheduled checks that catch corrosion or water damage before it eats away reserve capacity. Every change in use, every added load must be checked against the building's original rating. The hard lesson: redundancy is a system, not a single element. Safety depends on layers, ties, compartments, and constant vigilance. Today, millions of people live or work in buildings where a single failed connection or a missed inspection can tip the balance. Progressive collapse is not rare engineering trivia. It is an everyday risk. Safety depends on vigilance, not just concrete and steel. The real question: would you recognize the warning before the floor gives way?